Hi everyone, this is Tom Cherry Holmes, and I'm making a quick video here showing exactly how I made this program right here, which shows a colorful rendition of the Atari logo using display list interrupt effects on a Mode F screen. Simple enough. Let's get started. We'll need a terminal here so that we can do our cross-development work. I'll be using MAD Assembler, but you can use whatever you feel is important, whatever you wish to use. To start, we know that we want to use a Mode F display. This will give us 320 pixels across by however many lines we put in the display list. Normally this is 192, so that's what we'll use here as well. To get started, we'll actually poke right into Atari Basic for a moment, and we'll grab a display list that we can borrow for our Mode F display as a starting point. I can go to Apps, I can go to Atari 8-bit, we can go to DOS, and I'll just pick a standard copy of Atari DOS 2.0, nothing special. And then you'll notice that I have Basic enabled here. I'll simply boot it. And once we're booted here, I'm going to take and make a very simple little program that will actually just go into Graphics 8 and sit there for a moment so we can break out of it with the debugger and see what the display list looks like. So we want a full screen display, so we go Graphics 8, but we add 16 to it to turn on full screen support. And because this is full screen, the moment that the basic program ends, it will close the screen device, which will cause the screen to clear. We don't want that, so we actually want to just keep going in a loop so this screen stays active. So there's our blank Mode F display with the default color palette. We go ahead and break out, and we can see that we're basically just sitting here waiting in Basic's little loop here. And if I do a dump dlist, I can get a list of the elements which make up this display list. You can see there's not much to it. We've got 3 blank lines up here at the top, which are then followed immediately by a Mode F at address 8150, followed by 93 more lines of Mode F. Now, why is this the case? Well, it has to do with the fact that addresses to ANTIC has a 12-bit address counter, and thus, pretty much, long story short, anything that you point to or you should address in memory should ultimately deal in 4K boundaries. So if you need more than 4K worth of display space here, you go ahead and you allocate that space relative to your next 4K block jump here. So if you take and subtract 93 back from that times 40 bytes across for each line, we wind up with an address of 8150. At least this is how the operating system does it, and it prevents the need from needing to do jumps and all these sorts of things to make your display list work. So we'll just borrow this as is right here. And if we actually take a look at that address, we'll see that we have our 3 blank instructions. We have a load memory instruction for Mode F starting at 8150. And then a whole bunch of these, one right after the other, one right after the other, one right after the other, okay? And then it just completes. And then if you come down here, you'll see another one, another load memory instruction. See, right there, followed by the rest of the Mode F lines here. There are 192 of these lines in total. So how do we start off here? Well, let's make some space. I'll just go ahead and I've already got this. If you want to follow along, by the way, the code is actually up here on GitHub. So you can go to GitHub, you can grab a copy of it. I'll put a link of it in the description so you can see it here. Go to GitHub. Yeah. Just gently put this over here to the side for a moment. Atari Mode F logo. You can see the source code here in its glory, and you can study it yourself. So you can see what we're about to write. Cool, right? Okay. With that, pull that to the side here for a moment. So we basically go ahead, and I'll start with the first bits of this. You can use whatever assembler you wish. It really doesn't matter. You have full choice here. I'm going to use the mat assembler here. And we need a handful of equates to help us along here. To start off with, we need an equate for VDLST. This is the vector for the display list interrupt. It lives at 0200, and we also need the shadow location for where the ANTIC needs to point its display list pointer. That lives at address 230. In order to pull this off, we need color registers 1 and color registers 2. Color register 2 basically deals with the background, and color register 1 deals with the foreground. We can't use the shadow registers because we're doing display list interrupt tricks, and therefore we want to handle the color registers on ANTIC, which are write only, directly. T017, T018 respectively. We also want an equate for the WSync register. Any reads or writes to this register will cause the ANTIC to assert the processor to wait until the beginning of the next scan line. This is excellent for horizontal synchronization. So this lives at D40A. We also want the vertical count register. This tells us what scan line the electron beam is currently on. This lives at D40B. And finally, we need an equate for the NMI enable register. This register will allow us to assert and tell the ANTIC that it not only needs to deal with vertical blank interrupt processing, but it also needs to assert for each and every display list interrupt that it finds in the display list. If you do not set NMI enable here, the uppermost bit in NMI enable, DLIs will not get processed. So we'll go ahead and start. We want to start here at org 8150. Remember, that's where this piece of graphic data started here, because we're going to be taking and putting and inserting our graphic. Finally, we're going to go ahead and make another segment here, starting at 4000 for our actual program code. This is simple enough. All we have to do, tell ANTIC that we want to use our display list. And that's all we have to do to tell ANTIC that we want to use our display list that we will define down below. Then we want to take and do the same thing for our display list interrupt that we want to take and define. We want to store this in VDLST, just like that. NMI enable, loop, jump, loop. And finally, when that's all said and done, we don't need to do anything else. We just need to take and loop over and over and over. And that's the main part of our program. We need to define a display list interrupt, which is what's going to run every time that we hit a display list interrupt line in our display list. To start off with, it's going to be very simple. We're just going to take and pull the accumulator parameter off the stack because the operating system puts it there. We need to go ahead and pull it off. We need to do our thing, and then we need to take and put it back, we need to push pull just like this, and finally return from interrupt so that everything is nice and neat. Okay. We do this especially here because this routine is ultimately going to use the accumulator to basically load and store things. So we have to take and preserve what's on the accumulator and then put it back on before we actually take and leave our interrupt. So with that, there is that. There's our basic program ready to go right there. Now, we need to take and create output raw. How are we going to do that? Well, we need to take and go into our friendly little image manipulation program. In this case, I'm going to use GIMP, and I'm going to load a copy of the Atari logo right here. This is the Atari logo here. It just happens to be formatted as 320 by 192. So whatever we're doing here, since this is our target display resolution, this is what we do here. It's just a simple black and white image, as black and white as it possibly can be. Okay, got it right here, groovy. So now we've got that, but we need to take and process it. In order to process it, we have to take, and we'll go ahead and export this into temp so I have a copy of it local enough. So there's our 320 by 192. It's indexed color, which means if I take and set mode indexed, I set the number of colors to 2. And in point of fact, if we take a look, you see that it has a 1-bit color map. That means it has 2 colors maximum here. 320 by 192, 1-bit color map. We have to take and process this somehow. Okay? Our best way we can do that is to use a little tool called Image Magic to take and convert this into something that the Atari can understand. Convert Atari, we can use convert from the Image Magic toolkit here with an input file of Atari logo. We'll set the depth to 1 because that's going to be our output depth. And we're going to use the gray output module here. And we're going to take and output a file called output.raw. This is going to take this data right here and output it just as a solid stream of 1 bit per pixel data monochrome, straight up. That's all we got to do. And if we actually take a look at that, we'll see that it basically is just the raw monochrome data. You can see pixels that are filled all the way across as FFs here for all 8 bits and so on. So at least we know we're in the right ballpark here. And in fact, if we actually take a look at the size of the file that gets created, I need to clean up my temp directory. We'll see that it is exactly 7,680 bytes, which is the precise number of bytes that you need for a 320 by 192 display in mode F on the Atari. So everything lines up just fine. Finally, as part of this whole thing, we also need our display list. You'll see that we've defined our display list here as the DL label. So we have to go now and actually implement it. That's easy enough. Recall before that when we were looking at our display list here, we start off with 3 blank instructions. 707070, okay? Our 3 blank instructions, followed by our LMS instruction for loading from 8150. Okay? And we're just going to take and put a whole bunch. So hold on a second. I'm going to take and see if I can make this a little bit faster. Oh, quit it. Don't do that. Okay. Copy. 1. 2, 3, 4, 5, 6, 7, 8, 9, 10. So we already have one mode F in here. I'll take and pull it off of that line right there. No problem. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we'll take and grab it here. So 3, 4, 5, 6, 7, 8. Okay. 1, 2, 3, 4, 5, 6, 7, 8. And so that gives us all the way up to 9. Recall that we have 93 right here. This gets us up to 90. So this will give us the remaining 3 bytes right here. So that's the first block right there. Then we have to, of course, again, just like we did before, we have to do a load LMS to go to 9,000 here to reset ANTIC's address counter. 4F0090. Okay, so now we do that, and then we do this again. And this time, grab it again. This time I'll just take and grab that whole block. 1, 91, 92, 93, 94, 95, 96, 97. Finally, as is customary for most normal display lists, you need, after I fix that, you need a jump back to the start of the display list after your vertical blank to start the whole process again. And for this, we'll use the low and high directives to point to our low, to put the low and high bytes for our label DL right here, so that the assembler automatically calculates the address for that top portion of the display list. Finally, we need one more segment, since this is an automatically loading piece of software, with a word back to start program execution right here at this point in time. With all of that, we should now have everything that we need to go ahead and assemble this. MADS output, we'll call it logo XEX, logo S. Oop. It looks like I need to make one little adjustment right here on line 34. Oop, let me get rid of the commas here. Because unlike a C compiler, this assembler isn't very tolerant of commas just hanging off the end there. But it's easily enough fixed. So now we have 58 lines of source assembled in 2 passes, 7927 bytes out to output file. And we can test this really quickly to make sure that this works. We'll boot an image, we'll go to, come back here, I'll actually go to Z, go to temp, and right down here. Then we'll take and go so we can boot. And if everything goes right, we should see, and we do, we see our Atari logo now staring us in the face with a plain Jane Mode F display here. We do our dump dlist. We find that we have our display list looking very much like a standard Mode F display. Looking good so far, guys. What do you think? Okay, so now let's take and start applying this. Let's start doing the bits and pieces that we need to do to apply color to it. To start, we just need to come back in here for a moment. We need to add some stuff to our display list interrupt. And the content of our display list interrupt is actually very simple. what's going to happen is that a display list interrupt is going to be fired on each of these individual lines right here, and the color will be reset based on what we talk about here. So whenever the display list interrupt instruction is hit, it will take and stop what it's doing and jump over here to our DLI code right here. And at which point we can modify the registers of the GTIA to alter what color gets output on that scan line. Simple enough. All we really need to do, let's do this as simple as possible. Let's figure out where we are on the screen. Let's go ahead and wait for the next scan line to happen. Then immediately, let's take that value that we just loaded here and put it into colp F2. That's it. Bam. Okay, this should get us some color pretty quickly. Except it won't. Watch what happens. You'll see that nothing is fundamentally changed. And that's because we're not marking where the display list interrupts need to happen. And in point of fact, I'll change this to the default value of 40 so we can really drive this home. Let's go ahead, boot this in. Still nothing happening. Darn, why is this not working? Well, let's take a look. Let's look at how ANTIC is set up here. If we look at NMI enable here, we see that 40 is currently set. And that means that the ANTIC is only doing vertical blank interrupt processing. We can change that by altering this to C0. And if we boot again, you'll see that nothing has changed. But if I now take a look at ANTIC, you'll see that the NMI enable is processed, and now we have DLIs enabled. So the moment that we start triggering one, you'll start to see it change. So let's see if we can do that. Let's take and just change one of these. All we have to do to take and enable DLI for a particular display list interrupt is to set the highmost bit, which gives us CF in the case of 4F here. Oops. So now we have the DLIs turned on, and we have one DLI that gets set. Let's watch what happens. Again, not much happening here so far. Did I actually assemble that? Yeah, let's see. And yes, you're actually going to see something rather interesting here once we actually get here. Let's try this again. Boom. Okay, so now we have the DLI happens on the scan line after the DLI instruction hits. So that's why we have one scan line here that is still the standard default color right here. But you can see that we've changed the DLI going down the screen until the next vertical blank, at which point the operating system resets all the colors into the shadow registers and the whole process starts again. Ruby, right? Okay, let's continue. For the others, all we really need to do is take and turn on change those to 8F. And now you'll see that I've done this for every other. And I've I've deliberately left this guy alone, so a DLI will not be fired here. So we can see the point at which the LMS reload actually happens. We'll continue, reboot, reassemble, reboot. Let's see what this looks like. Okay, so you see right here, okay, even though the LMS happens here and the DLI doesn't happen, that happens to happen on an odd line, so you don't see the transition. Really doesn't matter, but for the sake of completeness, we'll take and change it anyway. But you can see right here, even at this point right here, we've got the rainbow effect changing color 2, which is the background here, and altering the hue of the set pixels on the display. And this is because of a peculiarity of how Mode F works in the first place. It's very much a sellotape-like effect. Any color changes that happen are applied over the double speed clock pixels here. So that's why this looks like this. To complete the effect, all we really need to do is change color 1. So if I take and switch this real quick to ColPF1, you'll see the opposite happen. Kind of interesting how this works. But not quite in the way that you think. See? ColPF1 only adjusts the luminance of a particular set of pixels. And again, this is because of a peculiarity of how Mode F works in the first place. So the two color registers, color 1 and color 2, or ColPF0, ColPF1, ColPF2, are both interplaying off of each other. And we're utilizing that for this effect. So let's go ahead and change this back, ColPF2, and what we're going to do, just to really drive the point home of how crazy this is, we're going to go ahead and store the same values from ColPF2 into ColPF1, and watch what happens as a result. Okay, so assembled, boot, logo. It disappeared. Freaky, huh? Okay. That should give you a pretty darn good visual representation as to the relationship of the two main color registers in Mode 2 and Mode F. So let's make our logo visible. The simplest way to do that, at least the most striking way I could find to do that, is to take the value that we store in ColPF2 and immediately invert it using the exclusive OR instruction. So with that, we go ahead, save that, we assemble the result, and we should have our completed image. What do you think, guys? There you go. And this is exactly how I put this whole thing together from start to finish. Thank you guys for watching, and as always, fun.